All right, at this point, we've pretty extensively studied dilations and how dilations work, all the properties therein. What we end up creating is something called similar figures when we do a dilation. So the side lengths are going to be scaled, either reduced or enlarged, but the angles will be the same. They'll be preserved when we do a dilation. So we say that the two images have the same shape, different sizes. Those are called similar figures. It's just a proportionality reduction or enlargement. So the figures are considered similar if all pairs of corresponding sides are proportional, meaning they have the same scale factor, and the angles are the same. This little squiggle here is our notation for similar. It's like what you see on the top of the congruent symbol. It's just that they're not equal, they're proportional, so that's why we don't have the equal part of that, but we'll use that little squiggle when we're talking about similar. So in the diagram below, we know that these two triangles are similar. You can use tracing paper to verify that everything is correct with our angles. So you just trace triangle ABC and slide it down just to confirm that angle A is in fact the same as D, and C is the same as F, and B is the same as E. Similarity rules work the same way as congruence rules in the naming, in that whatever's first should match whatever's first, second should match second, third should match third. So that order does matter with similarity too. For part B here, solve for the missing side lengths of both triangles and show your work. So whenever we're trying to solve for side lengths and similarity, we need to establish a pair of corresponding sides that we do know. And the corresponding sides that we do know here are AC and DF. Now it looks like they're corresponding, but looks aren't necessarily enough. We do need to confirm it with the names. So we want to find segment AC and confirm that in fact DF is named the same way, and it is. So because we know that, then we can use that as our scale factor. Just don't assume, because sometimes there's a reflection done as well, or a rotation that can mess you up. So always confirm that your thought on which two sides are corresponding by checking the names. So once I have that, since the dilation has occurred here for 10, 7, and 14, we know that our scale factor is going to be 2. So we can apply that scale factor of 2 to segment CB and get FE is equal to 16. We're just doubling. And if we know that we're doubling, then we can reverse that with segment DE and divide by 2. Or you can do it with a proportion. This is showing the proportion here, that segment AB divided by segment DE is going to be the same as taking AC and dividing by DF. So you can set it up as a proportion that way too. But once you know the scale factor, you can just apply the scale factor with division if you're going backwards, or multiplication if you're going forwards. Okay, so give a dilation of ABC that would guarantee that its image is congruent. So basically that's just saying, what's the scale factor have to be in order to make A prime, B prime, C prime the same as that larger triangle DEF? Well, we know that everything doubled, so if we just say a dilation by a factor of 2, then we'll be sure that everything has transformed as it's supposed to. So that last example is explaining the definition of similarity. What we're going to do to describe a similarity transformation is to say that there will be a transformation that maps one figure onto the other. It's either a dilation alone or a dilation in combination with other things. And I had just mentioned that a second ago, that there could be a reflection, there could be a rotation. So if we have other transformations as well, that's fine, but similarity is implying that there has been a dilation somewhere. All right, so if we can find a set of transformations that maps them, then we can technically say that there's been a similarity transformation. Exercise 2, given that ABC and DEF are similar, with congruent angles marked, give a transformation that would map the smaller triangle ABC onto DEF. Now, tracing paper can absolutely help you here. If you trace triangle ABC, and then you can physically spin it and flip it and make it work, what you will notice if you do that is that this is a rotation. So if I were to translate this triangle and pick it up so that point A lands on point D, this triangle ABC would now be up here, right? Because all I'm doing is sliding it this way, sliding it along the paper. So if I had this traced on tracing paper and I slid it along here, A would be matching point D. But it's not perfect yet. So the next thing I would want to do is rotate it so that segment AB lies on DE. And the reason I'd want to do that is so that B is matching up with E and C is matching up with F. And once that's done, I would just do a dilation. And the dilation is going to say to take segment DE, which is our new one, and divide it by segment AB, which is our old one. And that will give us our dilation factor. That factor is bigger than 1 because I'm dividing a bigger segment by a smaller segment. But the important part of it is I'm dilating the new image by the old one. That's always the process we want to use to identify a scale factor, is to divide the new by the old. So K equals DE over AB. All right, in exercise 3, in the following diagram, it's known that BCN and ACM are straight lines, and also that the two triangles are similar to each other. So we can give a similarity transformation here. Again, you can use tracing paper if you want to. What's going to end up happening here, if I'm mapping ABC onto MCN, that sounds like it's a reduction because I'm taking a bigger triangle and making it smaller. So we'll keep that in mind. But if I just rotated this larger triangle, if I had it on tracing paper and I held my pencil point on C and rotated it, what would end up happening is this BC ray would just be an extension of the CN ray. If you can try that for yourself, and you'll see that if you hold down your pencil point on C and rotate it, BC becomes an extension of CN. And likewise, AC becomes an extension of CM. So that rotation will work there. And because these are straight lines, we're rotating 180 degrees because all straight lines have a 180 degree angle. So we're not just saying rotate this time, we're able to give a very specific degree rotation here. So rotating around point C by 180 will give me extension rays. And then if I dilate, the factor would be the BC segment divided by the NC segment. And that's going to give me my dilation. Now, this is an interesting scale factor here because BC over NC would imply that we are having an enlargement scale factor. So I think that technically what we should have, and I'd like you to have it this way on your paper as well, we should have NC over BC because NC is the new and BC is the old. So new divided by old would say NC over BC, and that is going to give us our correct dilation factor, which would be less than 1 in that case. So make sure you have NC over BC there as your scale factor. Always new divided by old. All right, exercise 4, given that we have some more triangles on this grid, what's the scaling factor? So you can take any segments and divide them. It's easiest to use horizontal or vertical segments because you can just count them. DE is 6 units, AB is 4 units. So if we're dilating ABC onto DEF, then DEF is the new, ABC is the old. So we divide new by old, 6/4 is 3/2 or 1.5. And to give it similarity transformation, again, just pick a point and match it up. So take point B and line it up with E, or you could do A onto D or C onto F. As long as you have corresponding points translated onto each other, that's your first move. That should always be your first move. Then you can do a reflection or rotation to make it look the same. So if you reflect over this EF segment, so the first step puts B onto E, that would have BC lying on the same line as EF. So if you simply reflect the triangle over that line, then it'll be in the correct orientation. And finally, we do a dilation using a scale factor of 1.5 because we had already shown that that was the correct number for the scale factor. So we don't have to use a scale factor with segments this time. We can use actual numbers. But the process for a similarity transformation should be first translate to line up a point, then either rotate or reflect as necessary, and finally do your dilation. All right, exercise 5. A, B, and C are collinear, as well as AD and E, so those all fall in the same straight lines. It's known that BD is parallel to CE, so to give a dilation, we would say the scale factor would be, well, we have choices here, but we could take AC and divide by AB, and that will map it. And remember, it's ABD onto ACE, so ACE is a new, so I want to take one of those new segments and divide it by one of the old ones. Could also do AE over AD. Could even do CE over BD. There's always choices with that. So that'll give us our mapping, our scale factor. And to circle the proportion, that's correct. So AD over AE and AC over AB, we're looking for the incorrect one rather. The problem with this one, and we'll go back to the others as well, the problem with this one is AD comes from the small triangle and AE comes from the large one. But in the second fraction, AE comes from the large and AB comes from the small. You need to be consistent when writing your proportion. In choice 1, AC and CE are both from the large, AB and BD are both from the small, and they correspond. The angles, so angle A and angle ABD, angle A and angle ACE, that would be correct because the angles are preserved. So no problem with that proportion. And same thing here, angle AEC and ACE, that's here and here with the big triangle. ADB and ABD, those all match up, angles are preserved, so those are both fine too. So the only incorrect one is the one that had the proportion without corresponding sides.